How these black holes grow to such enormous sizes and how they impact the formation and behavior of the surrounding galaxy remains a matter of active research. Do they regulate star formation through feedback processes such as outflows and jets? Or do they merely grow alongside the galaxy without directly influencing its evolutionary path? Dark matter also adds a layer of complexity to our understanding of galactic evolution. While it is clear that dark matter halos provide the gravitational scaffold necessary for galaxy formation, the nature of dark matter itself is still unknown. Understanding how dark matter interacts with ordinary matter and how it influences processes such as galaxy clustering and the formation of cosmic filaments is essential for a comprehensive picture of galactic evolution. Additionally, the distribution and behavior of dark matter within galaxies, especially dwarf galaxies which are dark matter dominated, pose significant challenges and questions for cosmologists. Galactic mergers and interactions, common processes that profoundly shape galaxies, introduce further mysteries. While it is known that such interactions can trigger intense bursts of star formation, as well as significant morphological transformations from spirals to ellipticals, the exact outcomes of these events depend on numerous variables, including the mass ratios of the interacting galaxies, their relative velocities, and angles of approach. Simulations offer some insights, but the sheer complexity of these processes means that many details about how galaxies evolve through interactions remain unclear. Lastly, the impact of environmental factors such as a galaxy's location within a cluster or its interactions with the intergalactic medium adds another layer of uncertainty. Galaxies in dense cluster environments can undergo processes like ram pressure stripping, where their gas is stripped away by the intra-cluster medium, quenching star formation. How these environmental processes collectively shape galaxy evolution and diversity across different environments is a significant ongoing area of research. Together, these mysteries highlight the intricate and dynamic nature of galaxies and underscore the need for sophisticated observations, simulations, and theoretical advancements to unravel the full story of galactic evolution. Star formation, the process by which dense regions of molecular clouds collapse to form stars, is rich with complexities and unanswered questions. One of the primary unknowns involves the initial conditions and specific triggers that set star formation in motion. While it's established that regions within molecular clouds must reach high densities and low temperatures to begin collapsing under their own gravity, the precise mechanisms that drive these conditions, whether it be turbulence, magnetic fields, or external pressures such as shock waves from supernova, are still a topic of active debate. Understanding these initial triggers is essential for piecing together the life cycle of stars and the evolution of galaxies. Another intriguing mystery focuses on the formation of massive stars. These stars, with masses more than 8 times that of our Sun, pose a particular challenge because their intense radiation and powerful stellar winds should, in theory, inhibit further material from accreting onto the nascent star. However, massive stars do form, implying that there are processes at play that allow for the accumulation of such large amounts of mass. Theories suggest that mechanisms like disk accretion, where material spirals into the star along a rotating disk, and competitive accretion within dense stellar clusters might be involved. Yet observational evidence to fully support or refine these models is still required. The initial mass function, IMF, which describes the distribution of masses for a population of newly formed stars, is another area shrouded in uncertainty. The IMF appears to follow a specific pattern universally, with many more low-mass stars forming compared to high-mass stars. However, the reasons behind this distribution and whether the IMF varies significantly under different environmental conditions remain topics of intense study. Insights into the IMF could provide critical information on the formation and evolution of stellar populations and their impact on galactic dynamics and chemical evolution. Magnetic fields and their role in star formation add another layer of complexity. While it is known that magnetic fields exist within molecular clouds, their influence on the fragmentation of clouds and the subsequent stages of star formation is not well understood. Magnetic fields might support clouds against gravitational collapse or guide the flow of material, but capturing the exact nature and strength of these fields involves challenging observations and simulations. Feedback processes from young stars, such as stellar winds, radiation pressure, and supernova explosions, also significantly impact star formation. These feedback mechanisms can either trigger subsequent star formation by compressing nearby gas or hinder it by dispersing surrounding material. Balancing these opposing effects and understanding how they regulate star formation rates across different environments remains an ongoing challenge. Furthermore, the process of forming planetary systems alongside stars introduces additional intricacies. How protoplanetary disks evolve and give rise to planets in tandem with the host star's development involves complex interactions of gas, dust, and gravitational dynamics, many aspects of which are not yet fully understood. The suite of unknowns in star formation, from the initial triggering mechanisms and the complexities of massive star formation to the role of magnetic fields, feedback processes, and the IMF, underscores the rich and intricate nature of this fundamental cosmic process. Continuous advancements in observational technology, theoretical modeling, and computational simulations are essential for unraveling these mysteries and achieving a comprehensive understanding of how stars and their accompanying planetary systems come to be.